The right antenna you can gain a lot, and with the wrong antenna you can lose a lot. This is not only true for your received signal strength. It can also have a significant influence on your signal to interference level. Of course, you want to choose the right antennas for your project. This time we are giving away a little tool that helps you first to get some technical terms for your antennas sorted. Second, you can complement the related specifications. And third, and most beneficial, you will understand relations between the antenna properties. For example, you only know the gain of an antenna. What beamwidth would roughly correspond to it? Could you expect the radiation diagram close to the antenna? What effect could I achieve by tilting a directional antenna? Furthermore, sometimes you might want to get the radiation patterns in numbers, or you want to have a nice diagram plot for your presentation. We are Electronics Unmasked, and we got a tool for this. We start with the standards that are in the DNA of every radio engineer. You can find a lot of reference tables for this, but here is an easy to use tool for it. Let's have some examples. Radio amateurs are usually happy if their antenna VSWR is 1.1 or better. We can see immediately why. The reflection factor is only 0.048, which would correspond to a small cycle around the matching point in the Smith chart. Then it is no surprise that the transition factor is very close to 1. This means that almost the complete transmit power goes into the antenna. The corresponding return loss level is 26.44 dB. The transition loss level is only 0.01 dB. This is practically nothing, because usually you get more transition loss from connectors and adapters. Another example would be an antenna with a VSWR of 2. The return loss is then 9.54 dB, which means that about 1/10 of the power is reflected. The transition loss would be about half a dB in this case. Okay, we all wish that the transition loss should be less than that. However, in case you are using a long cable with adapters, you probably get more loss from this. On the right side of the sheet you can do the reverse calculations, starting with the return loss. Let's take 20 dB return loss, and again you get the corresponding values here. The second sheet gives us some interesting insights on beamwidth versus gain, and it tries to clear up the confusion with the units of measure that define the antenna gain. Here is the type of questions that you will be able to answer with it. How does the beamwidth relate to the antenna gain? Is antenna directivity and gain the same? We find antenna gain specifications in dBi and in dB and in dBd. Is it the same? Sometimes we get a linear gain factor. How does that relate? I have to admit, the stuff can be pretty confusing. Let me first try to sort the different dB values. The antenna directivity in dBi is related to a theoretical isotropic antenna that radiates evenly in all directions. Its directivity is 0 dBi. Since an isotropic antenna doesn't exist in practice, there is a second definition in dBd that relates to a half-wave dipole which has a directivity of 2.15 dBi or 0 dBd. In other words, a 10 dBd antenna has practically a higher directivity than a 10 dBi antenna. The exact difference is the set 2.15 dB. In case you get only a dB value for the antenna gain, you should be suspicious and rather assume dBis. Now let's see what the tool can do actually. We assume a Yagi antenna having a vertical beam width of 70 degrees and a horizontal beam width of 54 degrees. The resulting value for the directivity would be 10.38 dBi. And you get also the value in dBd here, which is always 2.15 dB less. Okay, fine so far. Now I need to tell you that an antenna can never have 100% efficiency. Of course, the conducting antenna material is not ideal, and there is always loss in the feeder network, the balloon, etc. In our example, we consider an efficiency factor of 92%. This yields then an antenna gain of 10.02 dBi. The difference between directivity and gain becomes clear now. Because of the efficiency, gain is always lower than directivity. The antenna gain is usually the important parameter in practice if you want to calculate the effective radiated power. And here I need to give you another important hint. Radio guys are talking about effective radiated power and effective isotropic radiated power. And you guessed it, the one is related to the dipole and the other one is related to the isotropic antenna. Don't confuse this, the difference here is also 2.15 dB. Just to complete the table, we give the corresponding linear gain factors on the bottom. I hope this will help you a bit to distinguish the different specifications that you will find for antennas. Our tool is using a simple approximation to compute the directivity and the gain from the beam width. However, it works well for almost all cases of antennas. The antenna beam width is per definition the angle between the points where the gain is 3 dB reduced. Finally, I want to give you another hint on that. The half-wave dipole is often confused with the so-called Hertzian dipole, which is named after the famous German physicist Heinrich Hertz. I need to mention that the Hertzian dipole is also a theoretical antenna that doesn't exist in reality, and its gain is different from the half-wave dipole, which is real. On the bottom of the sheet we have the properties for your reference. Usually we get measured antenna diagrams together with other specifications. Sometimes we only know the 3 dB beam width of an antenna or we want to have the radiation diagrams in numbers because we want to feed these into other tools. Our radiation pattern generator is able to create these. For instance, you can choose any 3 dB beam width and the tool will approximate the corresponding radiation diagrams. The polar plots are giving us the linear presentation of the diagrams, and the Cartesian plots are giving us the diagrams in dBi. Currently, we have our Yagi antenna parameters with 70 and 54 degrees beam width in the tool. We could change, for instance, the orientation. We can choose any other orientation between 0 and 360 degrees. We have 90 degrees vertical orientation. Let's change that to 120 degrees. And the horizontal orientation we change from 0 to 150 degrees. If we had another antenna with a different beam width, we also could change the beam width. Say from horizontal 54 to 90 degrees, or even 180 degrees. But let's go back to the 90 degrees here. And vertical we change from 70 degrees to 35. Already from the scale on the axis we can see immediately that it has now a higher directivity. And on the right side of the sheet here we get also the correct directivity as well as the front to back ratio of the antenna. What's left to explain here is that we can insert the side lobes level. The tool doesn't simulate the actual side lobes, it is just giving the maximum side lobe level. For planning purposes, this is usually the better assumption, because if you mount your antenna to a pole or a wall, you never know exactly the direction of your side lobes. Sometimes I'm using the given plot functions for presentations, because it is so easy to create any antenna diagram from it. In case we need the diagrams in numbers, we can also make our life easy here. We go to the bottom section where we find the diagrams in numbers. With a simple copy and paste, we can export the values. It's important here to copy only the values using the paste special. And that's it. With that method you can export to any spreadsheet or any text editor. In many cases there is room for improving your radio coverage by tilting your directional antenna. Let's say you want to cover the area next to your house with Wi-Fi. You got a directional antenna with 35 degrees vertical beam width for your router. You mounted the antenna to the building in about 5 meters height. Your desired range shall be 50 meters from the house maximum. From this little tool you get now a proposal to tilt your antenna. The down tilt for the best signal strength at the maximum range would be 5.71 degrees. The best signal to interference level for your router would be at 40.71 degrees down tilt. It depends now whether your range is limited by the received signal strength, which is the case in rural areas, or by the interference level from neighboring networks, which is typical for highly built-up areas. You know, in the city sometimes you find like 50 Wi-Fi networks in the neighborhood. The optimum values can be really different, as shown in the given case. We can assume that a good compromise is somewhere in the middle. Our tool is suggesting about 23 degrees here. Of course, the given method here is no rocket science. However, it can help to keep you and your neighbors happy. Now that you saved your neighborhood relations, we can look at our last interesting topic. Antenna diagrams are only valid for the far field. Usually, near-field patterns are far more complicated, and the coupling of unwanted interfering signals is stronger than you would expect it from the far-field diagrams. That's why we want to know the range of the near field. We will see that it is especially interesting in the case of high-gain antennas. We do a quick example. We are having a parabolic dish antenna with a diameter of 70 centimeters, which we use to receive a 5 GHz signal. As we know from what we said before, high gain antennas have a narrow beam width. Our question is now whether the narrow beam can prevent us from problems with an interfering transmitter which is located close to it. Our tool here tells us now that the near field range is about 8 meters. This means that we can expect the actual far field radiation diagram only in more than 8 meters distance. We might need to consider this when we operate other systems close to the antenna. In the case of low-gain antennas, for instance a half-wave dipole, you can consider the near-field range being less than 1 wavelength. Of course, you can try it out with the tool. Finally, I need to give you a general important hint on antennas. Antennas are reciprocal elements. This means that you get the same diagram in the receive and in the transmit case as long as there is no active elements like amplifiers in the antenna. So everything we talked through in this episode you can apply for the transmitter and the receiver case. The summary. Specifications of antennas can be confusing. I would be happy if I could help you a bit to unmess this. We talked through the properties that define the impedance matching, and you can use the little tool instead of tables. You always knew it, there is a relation between the gain and the beam width. Playing a bit with the inputs, the little tool gives you the right feeling for the correlation. We can generate approximated radiation diagrams from the beam width. We can use the diagram graphics and we can export the data. In order to optimize the performance of a wireless system, we can find an optimum down tilt for a directional antenna. The range and the interference level can be improved so that your Wi-Fi connection, for instance, gets more stable. Antenna radiation diagrams are usually defined and measured in the far field. We learned how to calculate in what distance we can expect the far field. Hope you enjoyed the episode and don't forget to download the tool. Occasionally I will publish some more interesting stuff on electromagnetic waves, but this will be in extra episodes. The coming regular episodes will bring further cool ideas for projects using the Arduino platform and complementary electronics. Now, stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.